Hello there, and welcome to this quiet corner of sleepy science. You found your way here most likely because you want your mind to drift into something soft, steady, and gently absorbing. Perhaps you'd like a story that keeps your thoughts occupied but not agitated, something to lull your curiosity instead of stirring it into restlessness. So tonight, we'll take a meandering journey into one of the most invisible yet all-encompassing subjects there is, the chemistry of nearly everything. A subject so vast that it touches every breath you take, every sip of tea, every flicker of thought, and yet it does so silently, patiently, almost humbly. From the hidden rhythm of atoms joining hands in the dark, to the faint, unseen chaos of molecules bumping against one another in endless motion. Our path tonight is one of invisible forces. Forces that shape not only the world around you, but the world inside you. I'll try my best to keep this as calm and soothing as possible. Though I should warn you, the universe has a way of being almost too interesting. It has a habit of surprising you just when you're ready to close your eyes. But even if your mind lingers wide awake, the worst that can happen is you'll fall asleep a little wiser than you were before. And if you enjoy this kind of gentle exploration, where curiosity is allowed to wander at a drowsy pace, a little support helps keep this sleepy corner alive and glowing. A like, a subscription, or even just a note about where you're listening from, it all keeps the fire burning slowly but steadily. I always love seeing how far this whispering trail of science travels, reaching listeners in all kinds of places, in all kinds of times of day. So, wherever you are, on a pillow, in a chair, under a blanket, take a slow breath in. Let the air settle into you, and then let it drift away. Release the clutter of today, and allow your attention to sink softly into the story ahead. Because tonight, we're going to peer into the smallest building blocks of existence. We're going to ask why some things flare with energy, why some cling together, why some remain perfectly still, and why others fall apart into sparks and light. All of this without rushing, without stress, just letting the mind wander through the quiet halls of matter. And of course, none of this is advice for your body or your health. Think of it instead as bedtime science, checked and friendly, the kind that keeps you company in the dark while making no demands on you except to listen and drift. Let's start with something very ordinary. Picture holding an object in your hand, a spoon, a leaf, a crumbly cookie. Now imagine dividing it, not with the clumsy limits of your kitchen knife, but with some perfect imaginary blade. Slice it in half, then again, and again, and again. Every time you cut, the pieces grow smaller until they're almost dust, until they're barely specks. And if you were to keep going, to cut and cut beyond all reason, you'd eventually reach a point where you can't separate it anymore, because you're no longer holding the spoon or the cookie at all. You're holding the smallest unit that still exists as matter. That is an atom. Atoms are the essential seeds of everything you know. Your blanket, your nails, your tea mug, even the very device on which these words glow, all of them are built from atoms. You yourself are a grand collection of them, walking, speaking, yawning, stretching. Each motion, each thought, each heartbeat is the performance of countless particles that together form the illusion of solid, continuous you. And yet, though they are unimaginably tiny, the story of atoms is anything but boring. Every atom has a family of three main characters: protons, neutrons, and neutrons, and electrons. Imagine an atom as a little solar system. The nucleus is the center, packed tight with protons and neutrons. The protons carry positive charge, the neutrons carry none, and together they form the heavy heart of the atom. Orbiting around them are the electrons, tiny and negative, whirling in invisible patterns called orbitals. But this isn't exactly like planets circling a star. Not really. Electrons are not little balls following neat paths. They are more like mysterious clouds, places where they might be, shadows of possibility, rather than predictable dots. To know where an electron is at any given moment is like trying to catch an introvert in a crowd. They're always just slightly beyond reach. The nucleus, by contrast, is a core of certainty. The number of protons there determines everything. One proton alone means you're hydrogen. 6 protons and you're carbon. Swap a proton and the atom becomes something entirely new, as though the name tag at the cosmic conference table was suddenly switched to a different identity. Neutrons, the peacekeepers, make sure the protons don't fly apart, because protons, all positively charged, want to repel one another. The neutrons slide in, offering neutrality and balance, holding the core together like diplomats smoothing tension at the table. And then we return to the electrons, the restless dancers. They hold negative charge and live in energy shells around the nucleus. The farther they are from the center, the more energy they contain. They're like the quick, eager ones at a party, always ready to leap higher with the right encouragement, a burst of heat, a spark of light. And perhaps most astonishing of all is that atoms themselves are mostly empty. If the nucleus were the size of a pea, the nearest electron would be floating hundreds of feet away. That means the solid things you feel, the ground under your feet, the chair beneath you, are not truly solid. They are webs of invisible forces, like a room filled with unseen walls, giving shape and resistance to the otherwise vast emptiness inside. Atoms are so small that it's almost impossible to comprehend. A single grain of sand contains more atoms than there are stars in the entire observable universe. And yet, every one of those atoms abides by the same ancient rules: attraction, repulsion, bonding, and rebellion. Alone, they can be interesting enough. Take helium, just 2 protons, 2 neutrons, and 2 electrons. It floats aloof and quiet, refusing to bond, always drifting apart from the crowd. Oxygen, on the other hand, is the extrovert, eager to pair up, forming bonds that sustain the breath of life. You could imagine atoms at a cosmic dance, helium in the corner, quietly sipping from its own glass, while oxygen spins with hydrogen in the middle of the floor, making water and commotion all at once. But atoms aren't always polite. Some are unstable, radioactive, their nuclei overstuffed and restless. They decay, releasing energy in little bursts or in dramatic cascades. Tiny though they are, this is what drives smoke detectors, what fuels the heart of the Earth itself, what powers stars as they burn. Even instability, even chaos plays a role in the grand design. What astonishes is how predictable all this becomes with understanding. Centuries of patient science have given us the ability to map out the rules of atoms, to know how they'll behave, to bend them to our designs. With this knowledge, we can create new medicines, craft new materials, send electricity running through wires, and coax tiny parts of reality into vast technological wonders. The periodic table, that ordered grid of squares, is our atlas to these characters. Each square, a personality, a set of habits, a role in the story of the universe. Some are eager bonders, some stubborn loners, some heavy and slow, some nimble and quick. The table is less a chart and more a grand cast list of cosmic actors, each waiting for its scene. And still, for all our knowledge, atoms retain their poetry. They obey the bizarre rules of quantum mechanics, where particles can be in two states at once, where simply watching can change the outcome, where cause and effect blur into mystery. They don't think, they don't know we're talking about them. But if they did, perhaps they would smile at their fame. Tiny, invisible specks that, without ever asking for attention, hold the starring role in everything. So here we are, afloat in a universe of empty spaces and subtle forces, of countless atoms dancing by the same laws they've followed for billions of years. Out of this emptiness comes something astonishing. Life, awareness, you. And all of it begins with the smallest unit, the atom, the little something that builds the everything. Let's pause for a moment to notice the electrons once again, the tiniest, most mischievous of the trio. Almost weightless, 2,000 times lighter than protons, yet filled with restless energy and character. If the protons and neutrons are the solid, dependable workers holding down the fort, electrons are the mercurial artists, unpredictable and full of flair. They whirl, they scatter, they leap into higher shells when nudged by light or heat, only to fall back down again, spilling their energy out as glimmers of color. Electrons, in many ways, are why chemistry exists at all. They're drawn to protons the way moths circle lamps, yet they never collapse inward. Their attraction is balanced by their perpetual motion. And unlike planets, which move on clear paths, electrons exist in hazy probability clouds. They are less like predictable planets and more like cats in a big house. You know the few places they're most likely to curl up, but you'll never quite be sure until you check. And so their orbitals come in different forms. Some are tidy and round, some shaped like dumbbells, others like bizarre abstract sketches. Layer upon layer, the shells build outward, each able to hold more electrons than the last. And always, electrons seek the lowest rung first, only climbing higher when forced or when excited. It is here, in these restless outer shells, that reactivity takes root. Atoms whose shells are full are calm, unbothered, content. Helium, neon, argon, these are the cosmic introverts. Quietly self-sufficient. But atoms with incomplete shells are restless, driven. Sodium with its one extra electron dangling loose. Chlorine with its desperate need for just one more. When they meet, it's chemistry's version of destiny. Sodium gladly hands off its stray. Chlorine seizes it, and together they become salt. The simple miracle sitting quietly on every table. When atoms begin their exchanges, a quiet drama unfolds. Sometimes they share, sometimes they give. Sometimes they steal, and all of it is powered by one desire: stability. A full outer shell is the comfort zone every atom seeks. Some get there politely, through covalent bonding, where electrons are shared like a snack between friends. Picture two children breaking a cookie into equal halves so that both are satisfied. That's the essence of covalent bonds. Oxygen and hydrogen, for instance, come together in this way to create water. Each hydrogen brings one electron. Oxygen brings two, and together they fit, completing one another. From this polite act of sharing springs one of the most remarkable substances in existence, a liquid that shapes our planet and sustains our lives. But not all atoms are so generous. Sometimes an atom craves electrons so fiercely that it takes them outright. This is ionic bonding, where one atom hands over its extra electron and another seizes it with relief. Sodium and chlorine play this game perfectly. Sodium, with a single restless electron, can't wait to be rid of it. Chlorine, just one shy of a complete shell, longs to fill the gap. When the two meet, the exchange is swift and decisive. Sodium donates, chlorine accepts, and the two are bound together by the invisible pull of opposite charges. The result is a crystalline lattice of sodium chloride, sparkling grains of salt, the very seasoning that graces every kitchen table. And then there is metallic bonding, which is less about tidy pairs and more about community. Imagine a potluck dinner where everyone sets their dish on the communal table, and soon no one remembers whose is whose. In metals, atoms release their outer electrons into a shared pool, and those electrons flow freely across the structure. This sea of electrons is what makes metals shiny, able to conduct electricity, and flexible enough to be bent and hammered without breaking. It is a subatomic neighborhood where resources are shared without fuss. And in that sharing lies strength and resilience. In each of these cases, the outcome is the same. Atoms searching for lower energy states, striving to settle into comfort. When bonds form, energy is released, like a sigh of relief at the end of a long day. When bonds break, energy must be absorbed, like the effort of prying apart two tightly held hands. Light a fire, and you see this principle in action. Energy is first used to break the bonds in wood, but once those bonds snap, new bonds form in the ash and smoke, and in doing so, release floods of heat and light. Sometimes the process is slow and subtle, like rust creeping across metal. Other times it is sudden and spectacular, like fireworks bursting into brilliant showers of color. Each hue, the signature of electrons excited and then tumbling back into calm. Bonding is not just chemistry's trick for holding matter together. It is the foundation of life itself. In your body, proteins fold into precise shapes because of covalent and hydrogen bonds. DNA strands cling together with delicate pairings that make memory and heredity possible. Every nerve impulse, every heartbeat, every thought relies on the careful choreography of ions moving across cell membranes. Without bonds, there would be no structure, no function, no life. And beneath it all is energy, the universal heartbeat. Energy drives every chemical transformation, every shift from one arrangement to another. Yet even when atoms are eager to bond, even when the outcome would clearly be favorable, they often need a little push to get started. This is activation energy, the initial spark required to overcome inertia and set things in motion. Picture two shy guests at a party who would make perfect dance partners, but stand awkwardly at opposite sides of the room. Unless someone gives them a nudge, nothing will happen. Take a matchstick. Within it lies everything necessary for fire: fuel in the wood, oxygen in the air, reactive chemicals waiting for their chance. Yet the match sits quietly, unchanged, until you strike it. The friction provides the activation energy. Heat floods into the tip. Molecules begin to vibrate more wildly. Bonds stretch to breaking, and suddenly, combustion roars to life. Without that strike, the match could sit for years, full of potential but locked in stillness. With it, the reaction cascades in moments. This truth runs through all of chemistry. Molecules prefer to remain in their comfortable arrangements until something comes along to disturb them. Sometimes that disturbance is a spark or a flame, sometimes a catalyst, sometimes simply time and pressure. Once nudged, though, they tumble into new configurations, releasing or absorbing energy as bonds are broken and reformed. Electrons are central in all of this. They are the restless instigators, the ones who make bonds possible, who carry energy, who leap between shells and release light as they fall. They are why metals shine, why salt is solid, why water dissolves so much of the world around it. They are also why we see colors at all. A strawberry appears red because its electrons absorb other wavelengths and reflect red back to our eyes. The sky appears blue because electrons in air scatter shorter wavelengths more effectively. Leaves glow green because chlorophyll's electrons interact with sunlight in just the right way. Even the sheen of oil on water, shimmering with rainbow hues, is electrons at play with light. And yet, despite how familiar their effects are, electrons remain strange. They belong to the realm of quantum mechanics, where the rules defy common sense. Electrons can behave like waves or particles, or like both at once. They can tunnel through barriers they have no right to cross. They can exist in multiple states until someone looks. Even scientists who spend lifetimes studying them describe electrons as slippery, elusive, almost mischievous. They are tiny mysteries that nevertheless shape the solidity of matter, the warmth of flame, the sparkle of fireworks, the beat of your heart. It is humbling to realize that thoughts themselves, the sentences forming in your mind right now, are electrical signals. Neurons pass information through tiny jolts of electrons fluttering across membranes, creating cascades of action that give rise to memory, language, imagination. Electrons are not just behind the colors of strawberries and the glitter of fireworks. They are behind the very act of you thinking about strawberries and fireworks. Imagine, for a moment, if atoms had personalities. They might describe their bonds the way people describe relationships. Some atoms are clingy, some generous, some adventurous, some solitary. Some prefer quiet pairs, others thrive in chaotic collectives. Yet behind all these quirks lies the same motivation: stability, the search for lower energy, the comfort of completion. When hydrogen meets oxygen, when sodium meets chlorine, when carbon bonds with itself to create the rigid lattice of a diamond or the soft sheets of graphite, the story is always the same: atoms seeking balance. Sometimes the bonds are mighty. Diamonds are made of carbon atoms, each locked into 4 covalent bonds in a rigid tetrahedral pattern, creating one of the hardest materials known. Other times, the bonds are fragile, like the faint hydrogen bonds that let water cling to itself, forming droplets and surface tension strong enough for insects to walk across. Yet whether strong or weak, each bond is part of the ceaseless work of building the world. And in all of it, energy flows, sometimes slowly, as in the corrosion of a forgotten nail, sometimes violently, as in the eruption of a volcano or the pop of a firecracker. Always it is the same basic play: electrons shifting, bonds breaking and reforming, matter rearranging itself to reach new states of balance. So when you hold something as simple as a match, or a glass of water, or a grain of salt, you are holding the product of countless atomic decisions. Tiny particles, empty space, invisible forces, and restless electrons, all conspiring to create the tangible world. Beneath the surface of every ordinary object is a hidden dance of stability and energy, a choreography both predictable and mysterious. And as you let your mind drift toward sleep, it's worth remembering that this invisible world is always at work. Even as you lie still, the atoms in your body continue their dances. Your neurons continue their flashes of electrons, and the chemistry of nearly everything hums quietly in the background. From the smallest electron leap to the glow of a star, from the bonds that shape molecules to the bonds that shape thought, the story is one of balance, motion, and connection. The universe is built on it. You are built on it. And in the stillness of this moment, perhaps you can feel it. The quiet, ceaseless work of atoms, weaving everything together. That spark, that little nudge that gets atoms moving, is where so much of the story begins. Imagine it as a boulder at the bottom of a hill. The boulder is your collection of reactant molecules, comfortable in their current spot, not in any hurry to go anywhere. To reach the other side of the hill, the product side, the boulder first needs a push. That uphill struggle is what chemists call activation energy, the effort required before the reaction can unfold. Once the boulder reaches the crest, it doesn't need any more help. Gravity carries it down with ease. Reactions work the same way. Once that threshold is crossed, the process often continues on its own, a cascade of changes unfolding with little encouragement. Some molecules require hardly any effort to get moving, while others stubbornly resist. That's why some substances sit quietly on your shelf for years, perfectly stable, while others flare to life at the smallest spark. It isn't simply a question of what molecules can do. It's about how much convincing, how much energy it takes to get them started. And once the reaction does begin, something important happens. Energy is either taken in or given out. This is the dividing line between two great categories of reactions: endothermic and exothermic. Endothermic processes are the ones that draw energy inward, absorbing heat from their surroundings, like a reaction that can only keep going if you keep feeding it fuel. Plants demonstrate this beautifully through photosynthesis. They take in carbon dioxide and water, but to transform those simple molecules into glucose and oxygen, they rely on a steady stream of sunlight. Without light, the chemistry grinds to a halt. The entire plant bends toward brightness, not out of longing, but because its survival depends on the intake of that energy. Another example hides in first aid kits. Instant cold packs contain ammonium nitrate sealed away from water. Snap the pack, mix the two, and the reaction absorbs heat from its surroundings, drawing warmth right out of your skin. The cold isn't being generated, it's being stolen from you, heat vanishing into the hungry chemistry inside the pouch. Exothermic reactions, on the other hand, are the generous ones, releasing energy into the world around them. Combustion is perhaps the most striking example. Strike a match, light a candle, and the hydrocarbons in wax meet oxygen. In moments, they rearrange themselves into carbon dioxide and water vapor, and in the process, they spill out heat and light. Explosions, fireworks, the warmth of a campfire, even the metabolism of food in your body, each is driven by exothermic generosity. Inside your cells, sugars like those in a banana are broken down carefully in steps, releasing energy little by little instead of all at once. Your body is a polite combustion chamber, regulating each release so you don't burst into flames with every snack. The energy flows into everything from blinking to dreaming, measured and managed by enzymes. Reactions can also shift direction depending on their circumstances. When water evaporates into vapor, the process is endothermic. drawing heat from the surroundings. That's why a wet shirt cools you on a warm day. The water molecules are taking warmth with them as they escape into the air. But when that vapor condenses, the process reverses, releasing heat in an exothermic burst. Clouds in the sky build and collapse with this trade, turning invisible vapor into droplets and giving warmth back to the air. These reversals are a kind of dance, one step absorbing, the other releasing, a perpetual back and forth tuned to the environment. It's tempting to think that only the spectacular reactions are energetic. A slow decomposition of leaves over months doesn't look like much, yet it is chemistry quietly reorganizing bonds. The same leaves ignited in fire undergo similar rearrangements, only in seconds instead of months. The drama is in the speed, not the substance. Energy moves whether in a rush or a whisper. Helping reactions along are the unsung matchmakers, catalysts. These are substances that don't provide energy themselves, but lower the barrier, smoothing the path so molecules can meet more easily. Catalysts are never consumed in the process. They simply enable it. Enzymes, the biological versions, are at work in every living cell, orchestrating processes that would otherwise be impossibly slow. Imagine your stomach trying to digest bread without enzymes. The starches would sit there stubbornly, unchanged for years. With enzymes, the process unfolds in moments. Catalysts act like facilitators at a gathering, making introductions, nudging the right bonds to form, and then stepping aside as if nothing happened. The idea of activation energy explains why certain substances feel so unstable. Molecules perched at high energy states need only the slightest trigger, heat, friction, or even the brush of time to tip into a new form. Explosives are the most vivid examples. They sit ready, their entry fee into reaction almost entirely paid, waiting only for the door to open. That's why volatile chemicals are kept in cool, dark spaces, why medicines wait in refrigerators, and why aerosol cans carry warnings about heat. It is all about managing thresholds, ensuring that the final push never arrives prematurely. In a way, chemical reactions mirror human restlessness. Just as we shift pillows to find comfort, atoms reorganize themselves in search of lower, more stable energy states. Some prefer warmth, some need coaxing, some ignite with a spark. Whether it's a candle's glow, a cold pack's sting, or the warmth of your breath, every transformation is the story of energy being shuffled from one form to another. Nothing is random. Each change is timed, balanced, and carried by the exact amount of energy needed in that moment. It's easy to overlook this hidden ballet. We light stoves, watch clouds drift, strike lighters, or see sunlight streaming into a room without ever noticing the atomic negotiations beneath. Yet, behind every flame, every breeze, every inhale, reactions unfold, sparked and sustained by energy's patient hand. Often, all it takes is a gentle push to begin. And when that push comes, acids and bases are often close by, stirring the mood. They are the chemistry world's great mood makers, able to fizz, change colors, or shift entire pathways of reaction with just their presence. Thought of as opposites, they're really partners in the same story, defined by how they handle two small but mighty ions, hydrogen and hydroxide. Water is a good place to start. It looks so calm, so ordinary. But even there, a quiet tug-of-war is always unfolding. At any given moment, a tiny fraction of water molecules break apart into hydrogen ions and hydroxide ions, only to recombine almost instantly. It's like a soft murmur in the background, a conversation that never truly ends. Into this delicate balance step the acids and bases. An acid tips the scale by donating hydrogen ions, flooding the scene with H+, while a base shifts the balance the other way, removing them or contributing hydroxide. Both play their part in altering the quiet equilibrium. This balance is measured on the pH scale, running from 0 to 14. Right in the middle, at 7, sits neutrality, pure water. Below that, acidity grows stronger with each step. Above it, basicity or alkalinity increases. What makes the scale fascinating is that it's logarithmic. A solution at pH 4 isn't just slightly more acidic than one at 5, it's 10 times more acidic. Drop to pH 3, and it's 100 times more. Suddenly lemon juice, with a pH near 2, feels like an acid powerhouse, while vinegar, a bit milder at around 3, still makes itself known. On the opposite end, baking soda at 9 is a gentle base, while bleach, climbing up to 12 or 13, becomes fiercely alkaline, reactive enough to corrode or burn. What makes acids reactive is their eagerness to give away hydrogen ions. Those tiny, charged particles don't take up much space, but once free in a solution, they interact with other molecules in all sorts of ways, altering structures, speeding reactions, or damaging tissues. Bases, by contrast, are tidy housekeepers. They mop up loose hydrogen ions or add hydroxide to neutralize them, restoring balance. This constant tug-of-war plays out not just in labs, but in kitchens, in our bodies, in the air above us. Take your stomach. Hydrochloric acid churns within, breaking down proteins, dissolving food, and keeping unwelcome microbes at bay. Too strong, and it could burn through tissue, but nature has a countermeasure. As food leaves the stomach, the pancreas sends in bicarbonate, a mild base, to neutralize the acidity. It's chemistry and conversation, one side sharp and cutting, the other smoothing and calming, each making sure digestion happens without disaster. In cooking, acids bring brightness and transformation. A squeeze of lemon livens a salad. Vinegar in a marinade tenderizes tough fibers. Acids in milk curdle it into cheese. Bases are rarer at the dinner table, but not absent. Baking soda, mixed with an acid like vinegar or buttermilk, releases carbon dioxide that lifts dough into airy bread. Without that bubbling exchange, loaves would fall flat, heavy and uninspired. One of the most satisfying demonstrations of this chemistry is neutralization. When acid and base meet in just the right proportions, they settle their differences. The fizz of vinegar meeting baking soda is a playful example, producing water, salt, and a rush of carbon dioxide bubbles. More extreme pairings can be dangerous. Mix bleach, a strong base, with vinegar, and you'll release toxic chlorine gas. A vivid reminder that while opposites attract, they can also clash. They don't always do so peacefully. This sensitivity to acidity or alkalinity is especially crucial inside living systems. Enzymes, those biological catalysts that make life possible, are fussy about their surroundings. Too much acidity or too much base, and they unravel, losing their shape, losing their power. That's why blood pH is held so tightly, around 7.4. Stray too far in either direction, and the balance tips into danger. Yet even at the edges of possibility, life finds ways. Some microbes thrive in volcanic pools, where acids would scald most creatures. Others live in soda lakes, where alkalinity soars beyond what seems survivable. Life adapts to the chemistry of extremes, finding niches where most would dissolve. Beyond biology, this tug-of-war stretches out into the environment. Acid rain born from sulfur and nitrogen compounds in the air lowers the pH of lakes and soils, stressing plants and animals. The oceans, too, are shifting. Their chemistry altered as carbon dioxide dissolves into the water, lowering pH in a process called ocean acidification. Car batteries rely on sulfuric acid to drive electrical current through controlled reactions. Textile factories use acids to bind colors into fabric. Bases in soaps and cleaners strip away grease. Indicators, like litmus paper or the humble red cabbage, provide vivid signals of these shifts, changing color as the balance tips. Watching a strip of litmus turn from blue to red, or a splash of cabbage juice glow pink or green, is more than a classroom trick. It's a glimpse into the invisible negotiations happening between ions. And through it all, balance is the theme. Acids and bases may seem like rivals, but together they form the push and pull, whether it's vinegar soothing a wasp sting, and acids calming a sour stomach, or bleach lifting a stubborn stain. The story is always the same. Ions shifting, electrons dancing, molecules rearranging themselves into something new. Heat and pressure join into the great manipulators of molecular behavior. To us, they seem like dials on an oven or gauges on a pump. But to molecules, they are the conductors of motion. Raise the temperature and particles speed up, colliding more often and more forcefully. Lower it and they slow into stillness. Every atom and molecule is vibrating. Add heat, and that jiggle grows more vigorous. Collisions more frequent. Reactions more likely. That's why bread bakes in a hot oven. Why food spoils more quickly in summer. Why your body speeds up its metabolism when fever warms it. Heat accelerates motion, and motion drives reaction. Pressure, especially in gases, adds its own influence. Compress molecules into smaller spaces, and collisions multiply. Increase the pressure, and reactions speed up, simply because particles can't avoid each other. That's how industries harness pressure to coax reluctant molecules together. As in the Haber process, where nitrogen and hydrogen, normally indifferent to each other, finally bond under extreme conditions to create ammonia, the foundation of fertilizers and much of our food supply, of heat reshaping the bonds that hold matter together. Molecules remain themselves, but their arrangements shift, loosen, or tighten depending on how much energy they hold. And at the extreme edges, life adapts again. Microbes at the bottom of the ocean endure crushing pressure and scalding heat near hydrothermal vents, thriving in conditions where chemistry is pushed to limits. From the steam in a kettle to the roar of a thunderstorm, the same principles apply. Heat adds speed. Pressure adds closeness. And together they guide molecules into new bonds and new states. Even lightning and thunder are chemistry and physics intertwined, charges separating in heated clouds, air expanding faster than sound when struck by lightning's heat, booming outward in a crack we feel in our bones. That intertwined energy adds bonds and states that play in space by the nearness of others. Heat lends them momentum. Pressure squeezes them into contact, and between the two lies the spark of transformation. It is the same story, whether in the rise of dough, the flow of a river, or the flicker of a flame. Always motion, always collision, always change. And as molecules collide, they often refuse to stay still in their new arrangements. They go forward, then backward, shifting in endless balance. Reactions rarely end in one direction alone. They settle into equilibrium, a kind of molecular truce, where movement never stops, but the scales stay level. So the forward steps and backward steps match one another until the scene looks steady from a distance. Hydrogen meets iodine to form hydrogen iodide, and at the same time hydrogen iodide splits back into its parts. What you end up with is a living mixture in which nothing seems to change overall, yet everything is shuffling under the surface. That is equilibrium, motion without drift. Because this balance is fragile, small changes in the surroundings matter. Temperature, pressure, concentration, and catalysts all tug on the rope. A simple piece of practical wisdom captures how a system responds. Henri Le Chatelier noticed that when a settled reaction is disturbed, it leans in the direction that softens the disturbance. If you raise the temperature of a mixture where one direction consumes heat, the balance shifts toward that heat-absorbing path. If you cool it, the opposite path becomes more favorable. If you add extra reactant, the system uses it up. If you remove some product, the system tries to replace it. It feels almost like a thermostat that clicks on when a window is opened to winter air. There's a lovely color lesson that makes this visible. Nitrogen dioxide is brown. Dinitrogen tetroxide is colorless. They interconvert. Leave them to find their balance, and you see a faint brown tint. Now cool the vessel. The tint fades because the colorless form is favored while heat is absorbed. Warm the vessel again. The brown returns because the darker molecule is produced. Nothing mystical is happening. The mixture is simply shifting to counter whatever you did to it, and your eyes get to watch the pivot. Pressure plays by the same principle, especially when gases are involved. Squeeze the volume smaller, and the system favors the side of the reaction that produces fewer gas molecules. Relieve the squeeze, and the side with more gas molecules becomes easier to maintain. Molecules, like people in a room, will crowd or spread depending on how much space there is to share. Concentration works similarly. Pour in more of one species, and the reaction adjusts to consume it. Remove some, and the reverse direction replenishes what is missing. These are not choices. They are the inevitable result of billions of collisions seeking a configuration that minimizes the shove you just applied. In living systems, this dance is essential. Your hemoglobin is a tiny lesson in equilibrium with every breath you take. In your lungs, where oxygen is abundant, the binding reaction is favored and oxygen loads onto hemoglobin. In your tissues, where oxygen is scarce, the balance tilts back and oxygen is released. No switches are flipped. No supervisor shouts instructions. Concentrations alone steer the binding toward what the body needs at that place and time. Another quiet equilibrium keeps your blood chemistry in line. Carbon dioxide dissolves into water to form carbonic acid, which can split into bicarbonate and hydrogen ions. Breathe faster or slower and you shift that balance. Retain more carbon dioxide and acidity rises. Blow off carbon dioxide and acidity falls. Your lungs and kidneys help manage this so that the pH stays near 7.4. It is a constant, gentle correction that never stops. Industry also lives by equilibrium. Consider the synthesis of ammonia from nitrogen and hydrogen. The reaction is reversible and stubborn. Chemists learn to pressurize the gases, warm them to a carefully chosen temperature, and introduce a catalyst. Pressure favors the side that has fewer gas molecules. Temperature is chosen to keep the rate high without destroying yield. The catalyst lowers the barrier, so the system reaches its balance more quickly. The result is a practical flow of ammonia, which becomes fertilizer, which becomes food. It is Le Chatelier's principle translated into harvests and cities. Equilibrium does not mean equal piles of reactant and product. It means equal rates in opposite directions. In some systems, the mixture is nearly all product. In others, it is mostly reactant. The position of that balance is set by energy. If one side is much more stable than the other, the balance sits close to it. If the two sides are similar, the balance sits somewhere in the middle. Either way, the rope looks still because both teams are pulling with the same strength. There is something quietly humane about this idea. Nature rarely likes extremes. Most systems do not sprint to an end and collapse there. They come to rest in motion, with forward steps and backward steps matched. Even a bottle on a shelf has exchanges, however tiny. Gas in the air is rebalancing itself all the time. Rocks, if you zoom the time scale enough, trade atoms and shift minerals until a new state is found. Equilibrium is a dynamic pause, the appearance of peace created by equal activity in opposing directions. Once you start seeing it, you notice balances everywhere. Ecosystems compensate for losses and surges. Markets resist shocks and then settle. Even a conversation finds its level as the speakers adapt to each other. Chemistry simply gives you a precise language for the same habit. Systems nudge back when pushed. Yet not every reaction chooses the path of patience. Some reactions are sprints. When energy pours out in a rush and gas expands too quickly for its surroundings to absorb the change, you get a spectacle. The chemistry is not different in kind. It is simply fast, confined, and abundant enough to be dramatic. An explosion is the sudden release of stored energy, joined to a rapid expansion of matter. Heat rises sharply, light blazes, gases surge outward, and a shock wave rips through the air. The cause can be chemical, physical, or nuclear. The common thread is speed. Combustion is usually behind the chemistry we call explosive. A candle burns politely because fuel meets oxygen in a controlled way. Give the flame more surface area, more oxygen, and a tight container, and the same reaction becomes violent. A thin cloud of fuel mixed perfectly with air will burn through its volume almost at once. The pressure jump is what you hear as a bang. Hydrogen in a balloon behaves this way. Before the spark, the gas is harmless. Touch it with a flame, and hydrogen begins handing electrons to oxygen. Bonds break and reform into water vapor. The new bonds are more stable, and the energy released is large. Because the mixture is already spread through air, the reaction front can sweep through quickly. The air is heated, expands instantly, and a pressure wave snaps outward. Loud, bright, done in a heartbeat. Even when there is no oxygen coming from outside, some molecules pack both oxidizer and fuel into the same structure. Trinitrotoluene is a famous example. On detonation, the molecule rearranges to make stable gases and heat in a fraction of a millisecond. The material seems calm when handled because the activation barrier is high. A detonator provides a precise shock that pushes a small region over the hill. From there, a supersonic reaction front races through the solid and turns it to hot gas and pressure before the surroundings can absorb the blow. If the reaction front is slower than sound, you have deflagration, like black powder. If it outruns sound, you have detonation, which does most of the mechanical damage. Everyday life hides smaller versions of the same story. Flour, harmless in a bag, becomes reactive if dispersed as dust and exposed to a flame. The tiny particles offer enormous surface area to oxygen, and the flame can sweep through the cloud in an instant. This is why mills take such care with ventilation and ignition sources. Aerosol cans rely on pressure and often contain flammable propellants. Heat them and pressure rises. If they rupture near a spark, the plume can ignite. Very hot oil can also flash to flame, and throwing water onto it is dangerous. Water sinks, flashes to steam, and launches burning droplets outward. A stovetop lesson in fast phase change and rapid expansion. Sometimes we harness the speed for good. Airbags inflate by a controlled chemical decomposition that produces nitrogen gas in less than 1/10 of a second. Mining and construction use stable mixtures that respond only to designed detonators. The point is not destruction. The point is to release energy quickly and predictably, so that rock moves, a chamber fills, or a structure falls way intended. Nature builds its own versions. Volcanoes trap hot gas and molten rock until the pressure is too great. Then the system finds relief in an abrupt release, carrying ash and heat high into the air. A small insect, the bombardier beetle, stores peroxide and hydroquinone in separate reservoirs. When threatened, it mixes them with catalytic enzymes in a reaction chamber. The rapid reaction produces heat and gas, and the beetle fires a boiling spray at its attacker. A miniature chemical cannon that would be right at home in a lab manual. What we call an explosion is not a different category of chemistry. It is chemistry with the rate dial turned far to the right. Break bonds, make new ones, move to a more stable energy arrangement, release energy. The only difference is how quickly, how much, and how confined the reaction is. Fireworks make this beauty visible. Oxidizers and fuels launch stars upward, then tiny packets burst. Strontium salts glow red, barium green, copper blue, sodium yellow. The colors are electrons falling back to calmer states and releasing light with a characteristic energy. You are watching orbitals empty their excitement into the night. From here, the path bends naturally toward the element that makes life's spectacular complexity possible in the first place. The most versatile builder is not the heaviest or the rarest. It is the quiet architect with 4 steady hands. Carbon links chains into rings, rings into frameworks, frameworks into spirals and sheets. It can hold once, twice, or 3 times. It can arrange the same set of atoms into different shapes with different properties. It is not glamorous by itself. It is glamorous in what it can make. Carbon's gift is catenation, the ability to bond to itself again and again. That one talent creates the vast library of organic molecules. Dress the carbon framework with different small groups and the personality of the molecule changes. Add a hydroxyl group and you have an alcohol. Add a carboxyl group and you have an acid. Add an amino group and you have the potential to build proteins. Straight chains, branch trees, closed rings, fused rings, aromatic rings with shared electron clouds that delocalize for unusual stability. From methane, a single carbon with 4 hydrogens, to proteins and DNA that contain countless atoms folded and wound into improbable elegance. The rules are consistent. 4 bonds around carbon, geometry that follows from that number, and a playground of shapes. Double bonds shorten and strengthen connections, and lock parts of a molecule into flatter shapes. Triple bonds are shorter still and carry more stored energy. Rearranging the same formula into different structures creates isomers. Butane and isobutane boil at different temperatures because shape matters, not just composition. Go further into three-dimensional detail, and you find mirror image molecules that biology can tell apart. Two enantiomers can smell different or act differently as medicines. Carbon's capacity for handedness underlies the exquisite selectivity of enzymes and receptors. Life is tuned to shape. If you zoom out again, the materials around you tell the same story of arrangement. Graphite is carbon in flat sheets that slide. Diamond is carbon in a rigid three-dimensional lattice. Same element, different architecture, opposite properties. At the nanoscale, rolled sheets become nanotubes with surprising strength and conductivity. Single sheets become graphene, a platform for electronics and sensors that keeps revealing new tricks. Plastics, whether praise or lament follows them, are long chains of carbon repeating units. Fuels are carbon with hydrogen, their bonds storing energy that can be released when oxygen accepts electrons and more stable products form. Carbon also sits at the center of the climate conversation. Carbon dioxide is simple in structure and powerful in effect. Without it, the planet would freeze. Too much and heat is trapped beyond what ecosystems can easily absorb. Chemistry does not argue. It counts molecules and measures how light and heat interact with them. The story then becomes one of cycles, sinks, sources, and how quickly we move carbon from rock to air, compared with how quickly nature can move it back. Underneath all of this is a deeper current that runs through rust, flame, battery, and breath. The trade in electrons is relentless. Wherever something is being oxidized, something else is being reduced. The names sound technical, but the idea is simple. When one species loses electrons, another gains them. You cannot have one side of the trade without the other. Electrons are not thrown away, they are handed off. Rusting iron lays this out in slow motion. Iron atoms give up electrons and become ions. Oxygen, helped by water, accepts electrons and is reduced. The resulting oxide is stable but brittle. Bridges, ships, and tools must be protected because the electron trade proceeds whenever moisture and oxygen are available. The same trade, sped up and guided, gives you combustion, batteries, and cellular respiration. In every case, electrons move from higher energy situations to lower ones, and energy is released along the way to do work or warm the surroundings. And so the thread continues, balances that settle themselves, outbursts that release what was stored, frameworks that build upon themselves, and tiny particles that carry charge from one species to another. The world is not random. It is busy, patient, and full of motives that can be measured. If you listen closely, you can almost hear it, the soft murmur of systems correcting themselves, the faint crackle of fast reactions, the quiet click of electrons finding their way to a more comfortable seat. Yet in a biological context, the speed and control of these electron trades is astonishing. Inside your own cells, a steady trickle of electrons moves in sequence along chains of proteins, each step releasing a small packet of energy that can be captured rather than wasted. The molecule being broken down, glucose, is loaded with chemical potential, like a coiled spring of carbon, hydrogen, and oxygen. Enzymes peel away electrons, passing them along in a carefully arranged order through the folds of the mitochondria. the structures sometimes called the powerhouses of the cell. With each handoff, a proton is pumped across a membrane, building up a gradient. That gradient itself is a form of stored energy, and when it is released, the cell uses it to attach a phosphate group to adenosine diphosphate, creating ATP. These ATP molecules are tiny rechargeable batteries that fuel muscle contractions, nerve impulses, and every flicker of thought. Oxygen waits patiently at the end of the chain to receive the electrons, becoming water in the process. Without that final electron acceptor, the queue clogs, the flow halts, and energy production collapses. Breathing, at its simplest, is the steady intake of oxygen to keep those electrons moving, and the exhale of carbon dioxide, the waste product formed when carbon is stripped from glucose. If this sounds familiar, it is because the same principles appear in the devices we slip into our pockets and plug into walls. A battery is nothing more than a carefully arranged playground for redox chemistry. One side, the anode, is eager to part with electrons. The other side, the cathode, is keen to take them. Connecting a circuit lets the electrons flow, and the energy of their movement powers lights, screens, or motors. A humble alkaline battery hides zinc at the anode, ready to oxidize, and manganese dioxide at the cathode, ready to reduce. Inside, ions shuffle through an electrolyte to balance charge, while outside, electrons march through wires, silently carrying power. The brilliance lies not in the violence of sparks, but in the restraint, the steady channeling of what could otherwise be chaotic. In a rechargeable battery, the story is even more elegant. Apply an external voltage, and the entire flow reverses. Electrons retrace their steps, chemicals are reset, and the battery is prepared for another cycle. It is a controlled dance of give and take that can be repeated hundreds or thousands of times, a technological echo of the cellular respiration and photosynthesis that have been balancing electron flows for billions of years. Indeed, in a leaf, the story runs in reverse. Sunlight strikes chlorophyll, lifting electrons to higher energy states. Water is split, oxygen released, and electrons pulled into a transport chain that eventually helps stitch carbon atoms into glucose. Where your mitochondria burn sugar to release energy, the plant's chloroplasts use light energy to manufacture sugar. Opposites, but tied by the same principle. Electrons shuttling through chains, energy transformed step by step, never lost, only rearranged. Every calorie you eat began as sunlight captured by a leaf, a photon turned into chemical bonds by redox chemistry. Beyond biology, humans have found countless ways to put this same principle to work. Electroplating, for example, is redox in action. A dull object is placed in a solution of metal ions. Current is applied, and the ions are coaxed to accept electrons and settle as a shiny metal coating on the surface. Jewelry gleams, car parts resist corrosion, and kitchen utensils are strengthened, all because electrons are persuaded to move in just the right direction. Even health relies on controlled redox. A glucose meter detects blood sugar by measuring electron transfers in a tiny sample of blood, while breathalyzers monitor alcohol by oxidizing it into measurable products. Water treatment plants use redox chemistry to strip contaminants of their dangerous forms or reduce them into harmless precipitates. In each case, the story is the same. One species yields electrons, another accepts them, and energy or structure shifts in the process. What makes these exchanges compelling is that they reveal the personalities of atoms. Some, like fluorine, are fiercely greedy, pulling electrons from almost anything within reach. Others, like sodium, are eager to hand electrons away, almost flinging them like gifts at the first opportunity. Chemists formalize these tendencies as ionization energy, the cost of plucking an electron away, and electron affinity, how much an atom wants to accept an electron. The hunger for taking one in. When a reactive donor meets a reactive acceptor, sparks can fly, sometimes literally. The one that loses electrons is named the reducing agent, because by its sacrifice, it reduces the partner. The one that gains electrons is the oxidizing agent, because by its appetite, it oxidizes the partner. This naming can feel backwards, but the logic is consistent. In every trade, both sides are bound. There is no oxidation without reduction, no giving without taking, no losing without gaining. Once you recognize this, you start to see redox everywhere. Rust spreading quietly across a bicycle frame is just iron surrendering electrons to oxygen. A spark jumping when you touch a doorknob is a quick redistribution of excess electrons built up on your skin. A fire roaring in a hearth is a symphony of bonds breaking and reforming, with electrons flowing into more stable arrangements and releasing energy along the way. Even digestion is a controlled cascade of redox, electrons moving from sugars and fats into carriers, then through transport chains, finally settling with oxygen. In every corner, chemistry is not static. It is in motion, a ceaseless stream of electrons moving from one atom to another, finding lower energy, finding balance, driving transformation. But speed matters, and not all reactions are willing to happen quickly. Many face steep energy barriers that slow them to a crawl. Left alone, hydrogen peroxide decomposes so slowly you could watch a bottle for years and see little change. Yet inside your cells, an enzyme called catalase breaks it down in microseconds, producing harmless water and oxygen. That difference is the work of a catalyst, a substance that offers a smoother path for the reaction. A catalyst does not get consumed. It does not alter the final outcome. It simply lowers the hill that reactants must climb, making the journey easier. In living systems, enzymes are the supreme examples of catalysts. Shaped by millions of years of evolution, each one is tailored to fit a particular molecule and coax it into reaction. Substrates slide into active sites, bonds are twisted or strained, and new products emerge. Then the enzyme releases them and resets, ready to repeat the feat. Without enzymes, life would stall. Food would remain undigested. DNA would not replicate. Muscles would not contract. The pace of chemistry would be too slow to support the delicate, continuous processes we call living. Even outside of cells, catalysts are indispensable. In car exhaust systems, catalytic converters transform carbon monoxide into less harmful carbon dioxide and break down nitrogen oxides that pollute air. In industrial plants, metals like platinum and nickel help hydrogenate oils, refine fuels, or manufacture countless synthetic compounds. The Haber-Bosch process that produces ammonia for fertilizers depends on iron catalysts to make a stubborn reaction feasible at scale. Without that one catalytic step, global agriculture as we know it would collapse. Zeolites, crystalline minerals with tiny pores, sort hydrocarbons in refineries, reshaping molecules into useful fuels. Palladium and rhodium enable precise transformations in pharmaceuticals, where even a tiny improvement in efficiency can save lives and resources. Green chemistry embraces catalysts for another reason. By reducing the need for extreme heat or pressure, catalysts make processes more sustainable, conserving energy and reducing waste. The subtlety of catalysts is easy to overlook. They do not flash or flare. They simply make things happen faster, with less effort. Some can even be designed to switch on or off in response to conditions, becoming active only in the right environment. Such smart catalysts hold promise for medicine, where a drug might be activated only in diseased tissue, or for materials that change properties when exposed to light or heat. Nature's own ingenuity has inspired chemists to create biomimetic catalysts, simpler synthetic versions of enzymes that mimic their efficiency. In every case, the principle is the same. Offer a smoother route, and chemistry follows. If catalysts are the quiet facilitators, then water is the stage on which so much of this chemistry plays out. With 2 hydrogens and 1 oxygen, it looks ordinary, but its behavior is anything but. Its bent shape creates polarity, a subtle tug of war in which oxygen holds electrons closer, leaving the hydrogens slightly positive. This uneven charge distribution lets water molecules cling to each other through hydrogen bonds. Attraction strong enough to give water its remarkable properties. Those bonds explain why water boils at a much higher temperature than similar small molecules, why it flows as a liquid at room temperature instead of evaporating away, and why it clings to itself and to other surfaces. Insects stride across ponds because water's surface tension is strong. Plants draw water upward against gravity because cohesion and adhesion allow it to climb thin tubes. Oceans and lakes buffer climates because water can absorb vast amounts of heat with only small changes in temperature, smoothing out extremes that would otherwise make Earth less habitable. Water even breaks a general rule of matter by expanding when it freezes. As ice forms, hydrogen bonds lock molecules into an open lattice, less dense than the liquid state. That is why ice floats, insulating the water below and protecting aquatic life through winter. If it sank, bodies of water would freeze solid from the bottom up, a catastrophe for ecosystems. The same polarity that allows hydrogen bonding also gives water its status as the universal solvent. Salt, sugar, gases, acids, and bases dissolve readily because water molecules surround and separate their ions or polar groups. Without this property, blood could not carry nutrients, cells could not flush waste, plants could not transport minerals. Where water is scarce, life struggles. Where water is abundant, chemistry flourishes. Yet water resists mixing with non-polar substances like oils. Soap bridges that gap, one end binding to grease, the other to water, forming droplets that can be rinsed away. This duality underpins much of biology. Cell membranes, made of molecules with polar heads and non-polar tails, arrange themselves into bilayers in watery environments, creating barriers that hold life together. DNA and proteins fold in shapes stabilized by the way water interacts with their parts. Photosynthesis itself begins by splitting water, liberating electrons that help build sugars. Oxygen, the byproduct, drifts into the air for us to breathe. Each inhale is a quiet reminder of water's central role in the story. Water shapes landscapes too. It erodes mountains, digs canyons, carries sediment, and cycles endlessly through evaporation, condensation, precipitation, and runoff. It is at once stable and reactive, capable of acting as an acid or a base depending on context. Despite its abundance on Earth, only a fraction is fresh and accessible. And in the search for extraterrestrial life, water remains the beacon. Find liquid water, and you find the potential for chemistry that might one day resemble biology. And beneath all this, matter itself reveals its many moods. Solids are particles locked in place, vibrating but fixed. Liquids are particles sliding around one another, adapting shape but holding volume. Gases are particles flying free, filling whatever space they occupy. Add enough energy, and electrons are stripped away, leaving plasma, a churning soup of charged particles that makes up stars and lightning. Remove energy, and the process reverses. Gas condenses into liquid. Liquid freezes into solid. Every state change is a shift in energy, not in identity. Water is still H2O, whether as ice, liquid, or vapor. Iron is still iron, whether molten or rigid. States of matter are simply ways of arranging particles, responses to heat, pressure, and motion. When you look closer, the transitions between states of matter are less like flipping a switch and more like sliding along a spectrum of energy. Particles vibrate, loosen, and escape their structures, not all at once, but gradually, with some molecules breaking free sooner than others. That's why ice can melt slowly in your glass, solid and liquid coexisting in a shimmering boundary. Or why water boils in bubbles, rising through liquid still cooler than the vapor above. These boundary regions are rich with complexity, mixtures of states, reminders that the universe doesn't always conform to neat categories. And beyond the familiar quartet of solid, liquid, gas, and plasma, there are stranger states lurking in the extremes. Cool atoms to just a whisper above absolute zero, and they lose their individuality, merging into a single quantum wave called a Bose-Einstein condensate. Heat certain fluids in special ways, and they flow without friction, becoming superfluids that climb walls or seep through barriers, as if gravity and viscosity were afterthoughts. These states are rare in nature, but they reveal something profound. Matter is not fixed in its identity. It is a dancer, changing costume, a performer shifting role, depending on the stage of temperature and pressure. These transformations are not just curiosities, they are tools. By manipulating states of matter, humans have learned to shape the world. Refrigeration depends on the easy shift of liquids to gases and back again, absorbing and releasing heat. Metallurgy hinges on melting ores, letting atoms move freely before cooling them into new, stronger arrangements. The energy sector draws on the controlled burning of gases and liquids, the plasma arcs of welding, the steam driving turbines. Every shift, every transition, is chemistry in motion, a reminder that even the most solid-seeming material is only temporarily at rest. Think of the everyday drama hidden in your kitchen. The snap of frozen vegetables thawing into pliant greens, the swirl of water vapor rising from a kettle, then condensing against a window pane. The crust of bread forming in an oven as starches gel and proteins harden, locking in aromas. Each step is a story of particles gaining or losing energy, of bonds loosening or tightening, of matter exploring its possibilities. It is easy to overlook because it feels so ordinary, but it is the same principle that shapes stars, fuels engines, and sculpts landscapes. At its heart, chemistry is not about static lists of substances. It is about these ceaseless movements, the endless redirection of energy, the shifting arrangements of matter. Redox reactions hum quietly in your cells and in your batteries. Catalysts nudge reluctant molecules into motion, unseen but essential. Water bends rules to hold the fabric of life together, and states of matter remind us that nothing is locked, that change is the natural condition of the universe. The wonder is that all of this happens with such grace. Electrons flow, as if they were meant to wander. Molecules collide and rearrange with a kind of inevitability, guided not by intention, but by probability, energy, and the laws of physics. It is choreography without a choreographer, a dance written into the nature of particles themselves. From the slow creep of rust to the flash of lightning, from the rising dough to the beating heart, it is chemistry that carries the rhythm. And through it all, there is a strange harmony. For every electron lost, another is gained. For every bond broken, another is formed. For every structure that melts away, another takes its place. Nothing is destroyed, only changed, recycled, and reimagined at scales from the microscopic to the cosmic. It is a balance so complete that you are part of it without realizing. Every breath you take feeds electrons into chains. Every bite of food fuels molecules. Every drop of water in your veins participates in reactions stretching back to the origins of life. In the grand view, chemistry is not confined to labs or classrooms. It is the story of the universe expressing itself through transformation. The rocks under your feet, the stars overhead, the cells in your body, the circuits in your devices, all are bound by the same principles. Electrons moving, matter shifting, energy flowing, everything in motion. It is a quiet reminder that the world is not static, not fixed, not finished. It is alive with unseen reactions, a ceaseless unfolding of possibility. To listen to this story is to begin noticing the hidden patterns all around you. The fizz of soda becomes an echo of gas laws, the shimmer of a rainbow an interplay of water droplets and light, the warmth of a fire a stream of electrons seeking lower energy states. Even the silence of a sleeping forest is not truly still. Beneath the bark, within the soil, inside each cell, chemistry is always at work. The molecules never stop. The dance never ends. Matter never stands still, no matter how solid or still it looks to our eyes. Even when molecules seem frozen in place, they are vibrating, quivering with motion too small to see. When energy is added, those motions increase. When energy is taken away, they slow. Eventually, a liquid may harden into ice, or a gas may condense into liquid, or something stranger still may happen. A solid may vanish directly into vapor, skipping the liquid stage entirely. That's sublimation. The reason a block of dry ice steams away into a misty fog without ever becoming a puddle. In reverse, deposition paints delicate lace on windows in winter, as invisible water vapor in the air crystallizes directly into frost. These changes are known as phase transitions. They don't alter the identity of the substance. Water remains water. Carbon dioxide remains carbon dioxide. But they change how the particles are arranged, how tightly they hold each other, and how much freedom they have to move. In ice, molecules lock into a crystalline grid. In liquid, they slide around one another in a restless shuffle. In vapor, they fling apart, racing through space with little regard for their neighbors. What makes the difference is energy. Temperature, the measure of average kinetic energy, tells us how fast particles are moving. Pressure, the force pressing them together, dictates how closely they crowd. Together, the two determine whether matter rests as solid, liquid, gas, or something in between. The interplay of temperature and pressure can be mapped, and those maps, phase diagrams, are full of surprises. Water's diagram is particularly odd. Most substances solidify when squeezed under pressure, but ice has a rebellious streak. Press it hard enough, and it melts instead, the molecules slipping past one another more easily under compression. This quirk is what makes ice skating possible. The blade presses down with enormous pressure over a narrow strip of ice, forcing a thin sheet of liquid water to form beneath. The skater glides not over solid crystal, but on a self-renewing film of meltwater. Physics lending its hand to elegance. What's striking is that even the simplest examples of matter, the glass in your hand or the steam rising from a kettle, are engaged in ceaseless negotiation with their environment. Molecules respond instantly to shifts in temperature and pressure, reshuffling themselves, adjusting, trying on new roles. To sip from a cooling cup of tea is to witness this process. Steam condenses into droplets against the porcelain rim. Liquid molecules lose energy as they radiate heat, and ice cubes slowly release stored coldness into the brew, melting but never ceasing to be water. Nothing vanishes, it only moves through forms. The rhythm of matter is not destruction, but transformation, as predictable as the sun's rising. And yet, not all chemistry is about dramatic changes or violent reactions. Some of it is about coexistence. Not every mixture creates something new. Sometimes, substances simply share space, weaving around each other, mingling without truly blending, or dissolving into a uniform whole without altering their essence. This is the chemistry of mixtures, the quiet cousin of reactions. A mixture is not a new substance, but a gathering. Take a simple cup of tea. Hot water seeps through the leaves, carrying pigments, caffeine, and fragrant oils into solution. But the water itself remains H2O. The molecules extracted from the leaves remain themselves as well. The flavor of the tea is simply the sum of these ingredients suspended together, a temporary alliance of molecules that can, if pressed, be separated again. That reversibility defines mixtures. Unlike chemical reactions, which forge new bonds and new substances, mixtures allow each participant to keep its identity. Some mixtures are seamless, homogeneous. Dissolve salt into water, and the sodium and chloride ions scatter evenly among the H2O molecules. No matter where you dip your spoon, the taste is the same. Other mixtures remain patchwork, heterogeneous. Granola clusters in milk, oil floating above vinegar, soil blending stone and organic matter. They are not uniform. Their parts cling to individuality. And yet both types, uniform or uneven, make up much of daily life. From the air we breathe, a gaseous solution of nitrogen, oxygen, carbon dioxide, and trace gases, to the steel in our buildings, a solid solution of metals fused into strength. Solutions, suspensions, colloids, each tells a different story of how particles can coexist. A solution is stable. Its solute dissolved so thoroughly it cannot be seen. A suspension is less tidy, cloudy with particles large enough to scatter light, destined eventually to settle. A colloid floats in between. Milk with its proteins and fats dispersed invisibly, but able to scatter light. Fog with its suspended droplets. Mayonnaise, stabilized by egg yolks emulsifiers, resisting separation. Chemistry has a subtle beauty here, a dance of togetherness without merger. And mixtures remind us that chemistry isn't always about drama. Sometimes it is about presence. Oil and water may refuse each other, forming separate layers. But add a bridge, a molecule with both polar and nonpolar sides, and they can be coaxed into a truce. Emulsifiers turn salad dressing creamy. Soaps bind grease to water. And milk holds its colloidal secret long enough for us to drink it down without thinking. These are not explosions or transformations. They are acts of balance, of molecules choosing proximity without surrendering self. Even the distinction between physical and chemical change rests here. Shredding cheese, boiling pasta, crushing ice, these are physical changes. The molecules are unchanged, only rearranged in space. Bake a cake, however, and you leave the realm of mixtures. Heat drives chemical changes. Sugars caramelize. Proteins cross-link. Gases expand. And what emerges is no longer the sum of the ingredients, but something wholly new. The difference is permanence. Physical changes can often be reversed. Chemical changes cannot. And yet both exist side by side in the kitchen, on the factory floor, in the soil beneath our feet. Everywhere, separation and combination coexist. Mixtures can be pulled apart through physical means. Salt reclaimed by evaporation. Sand filtered from water. Crude oil distilled into fuels. Nature, too, sorts and blends. Seawater carries salts in solution. Clouds scatter droplets as colloids. Blood flows as a suspension of cells in plasma. The chemistry of coexistence is as essential as the chemistry of reaction. And then there is speed. Some reactions unfold with the patience of centuries. Rust creeping over iron. Diamonds slowly shifting toward graphite. Others happen so fast they seem instantaneous. A spark leaping from a match. A firework scattering into color. A gas exploding into expansion. Speed matters. The rate of a reaction dictates whether a process is gentle or violent, useful or dangerous, nourishing or destructive. Temperature plays the conductor's role. Warmer molecules move faster, collide harder, and more collisions means more opportunities for bonds to break and reform. Concentration is another lever. More particles packed into the same space means more collisions, more chances for change. Surface area matters too. Crush sugar into powder, and it dissolves faster. Grind spices, and they release their aromas more quickly. Even the orientation of a collision counts. Not every bump between molecules results in reaction. Sometimes it takes just the right angle, just the right moment, like a perfect high five amid a crowded room. And sometimes the system needs help. Catalysts step in as guides, lowering the energy hill molecules must climb, offering shortcuts that save time and effort. They are never consumed themselves, only reshaping the path so others can move more freely. In your body, enzymes play this role with extraordinary precision, transforming what would be sluggish processes into reactions fast enough to sustain life. Without them, digestion, DNA replication, even the spark of thought itself would falter. Catalysts aren't flashy, but they are indispensable. In industry, they are the reason fertilizers can be produced at the scale needed to feed billions. Iron in the Haber-Bosch process quietly allows nitrogen and hydrogen to unite into ammonia under conditions that would otherwise be impractical. In your car's exhaust system, precious metals like platinum and rhodium convert toxic gases into safer ones before they drift into the air. And in your body, enzymes are the constant companions of every heartbeat, every breath, every blink. One of the most striking examples is catalase, an enzyme found in nearly all living cells. Its task is to neutralize hydrogen peroxide, a harmful byproduct of metabolism. One molecule of catalase can break down millions of hydrogen peroxide molecules per second, transforming them into harmless water and oxygen. It's chemistry on fast forward, invisible to you, but essential to life. Even in a slice of potato or a piece of liver, you can watch catalase at work if you add peroxide. The fizzing bubbles are oxygen being released, evidence of enzymes working tirelessly behind the scenes. But catalysts do more than accelerate. They shape possibility itself. By lowering the activation barrier, they make reactions viable at conditions that would otherwise be too cold, too slow, or too energy-intensive. They allow chemistry to flourish where it would otherwise stall. Imagine life without enzymes. Food would rot inside your stomach before you could digest it. DNA would sit idle, unable to copy itself. Energy would trickle instead of flow. Life depends not just on chemistry, but on chemistry fast enough, precise enough, and gentle enough to sustain the fragile balance of living systems. And this brings us naturally to water, the quiet giant of chemistry. For all the exotic compounds and complex reactions, it is water that makes them possible. With just 3 atoms, 2 hydrogens, and 1 oxygen, it bends the rules in ways that defy expectation. Its polarity, the unequal distribution of charge across its V-shaped structure, makes it a magnet for other molecules. Its ability to form hydrogen bonds ties it to itself and to countless other substances, shaping everything from climate to cellular function. Hydrogen bonding grants water unusual powers. It should boil at a far lower temperature, yet remains liquid across a wide range. Its cohesion allows it to climb plant stems, to bead on waxy leaves, to form droplets that cling before they fall. Its high heat capacity makes oceans into vast thermal sponges, moderating climate, softening extremes, keeping the planet habitable. And its strangest trick, expanding as it freezes, keeps ponds and lakes from solidifying from the bottom up. Ice floats, insulating the water below, preserving life through winter. A quirk of geometry, a cosmic stroke of luck, without which ecosystems would collapse. As a solvent, water is unmatched. Salts, sugars, gases, all dissolve readily into its embrace. Nutrients travel in it. Toxins are flushed by it. Blood carries its cargo through its flow. Inside your cells, every reaction takes place in watery surroundings. Proteins fold in its presence. DNA strands stabilize in its bath. Even the oxygen you breathe was once part of a water molecule split by sunlight in photosynthesis, released to the air so you could inhale it. Life is not simply adapted to water. It is built on it. Beyond Earth, the hunt for life begins with the hunt for water. The icy oceans of Europa and Enceladus, the underground reservoirs of Mars, the vapor plumes caught in distant atmospheres, all stir excitement not because of water itself, but because where there is water, there may be chemistry, and where there is chemistry, life might follow. It is no coincidence that your own body is mostly water, that your cells are sacs of liquid, that your brain floats in fluid. For all its transparency, water is the most vital actor in chemistry's play. But matter is not limited to the familiar trio of solid, liquid, gas, with water as their exemplar. Add enough energy, and atoms strip away electrons, forming plasma, the state of stars, lightning, neon signs. Pull energy away, and exotic states emerge. Bose-Einstein condensates, where particles merge into quantum unity, or superfluids that creep up the walls of containers. Matter's forms are more varied than daily life suggests, each one a new choreography of particles responding to energy and pressure. Still, whether solid, liquid, gas, or plasma, the underlying truth is motion. Molecules vibrate, spin, collide, separate. Change is constant, but never random. Heat and pressure dictate the tempo. Catalysts offer shortcuts. Solvents create space, and time itself stretches or compresses the pace of reactions. Rust may take years to creep across iron, while combustion consumes fuel in seconds. Photosynthesis unfolds in the quiet patience of a leaf, while a rocket engine turns hydrogen and oxygen into water in a thunderous instant. Reactions are stories of timing as much as composition. Too slow, and a product may never form. Too fast, it may detonate with destructive force. In between lies the harmony chemistry prefers, reactions tuned to conditions, guided by balance. It is here, in this rhythm of change, that life has found its niche. Biochemistry is the most intimate expression of this rhythm. Unlike the loud theatrics of explosions or the quiet elegance of mixtures, biochemistry hums steadily in the background. It does not need drama. It needs precision. Every second, proteins fold, enzymes catalyze, DNA replicates, and ATP fuels. Without this ceaseless orchestration, there is no thought, no breath, no heartbeat. The chemistry of life is not about spectacle, but about reliability. It is chemistry wearing the disguise of constancy, yet no less miraculous for it. Proteins serve as the workhorses, their shapes dictating their functions, enzymes to catalyze, structural proteins to support, transport proteins to carry, signaling proteins to communicate. DNA holds the blueprints, long strands of four-letter codes spiraling into endless combinations. ATP carries energy in compact rechargeable packets, breaking bonds to release power and reforming to store it again. Together, they weave metabolism, a web of destruction and creation, breaking down molecules to release energy, building up molecules to form life structures, all interconnected, all balanced. This metabolism is less like an explosion and more like a city buzzing with traffic. Molecules shuttle down pathways, some heading toward construction sites, others toward power stations, still others recycled into new forms. Feedback loops regulate the flow. Enzymes act as traffic lights. Signals coordinate the pace. The system doesn't crash because regulation holds it steady. Too much product and the reaction slows. Too little and it speeds. It is chemistry with foresight, chemistry aware of its own balance. And though it hums quietly, biochemistry is no less dramatic. A misfolded protein can cause devastating disease. A single error in DNA replication can ripple outward through generations. An enzyme missing or malfunctioning can halt entire pathways. These failures highlight just how finely tuned life's chemistry is, how delicate the equilibrium must remain. Yet in its precision lies resilience. Cells adapt, repair, adjust, finding new balance just as any system at equilibrium does. So from ice skating blades to enzymes in your cells, from frost on windows to fireworks in the sky, from the fizz of soda to the metabolism of glucose, the same rules echo. Energy moves, pressure shapes, catalysts guide, and matter changes form. Chemistry is not a story of chaos or chance. It is a story of rhythm, of balance, of timing. Heat, pressure, and energy do not simply drive change, they choreograph it. And everywhere you look, from a cooling cup of tea to the stars burning overhead, the dance of chemistry unfolds, ceaseless, orderly, and astonishingly beautiful. Life has a way of holding itself together. Even when conditions shift, even when the environment becomes harsh or unpredictable, enzymes can alter their efficiency, pathways can reroute, and cells can adapt in astonishing ways. That resilience is part of what makes life so persistent, appearing not only in gentle temperate climates, but in boiling hot springs. in the deep-sea trenches where pressure would crush a submarine, in frozen deserts of ice where sunlight is rare. Biochemistry, the quiet machinery of life, thrives almost everywhere. And at the heart of it all, binding every process together, is carbon. The universality of life's chemistry is striking. Whether you peer into a single-celled bacterium under a microscope, or consider the enormity of a blue whale gliding through the ocean, the same language of molecules speaks in both. DNA follows the same code. ATP carries energy in the same way. Proteins are built from the same 20 amino acids, folded into precise shapes that determine their function. Life does not reinvent its foundations for every new species. It takes the same basic toolkit and modifies, refines, and extends it, weaving countless variations on a theme. This consistency tells us something profound. Once chemistry found a path to stability and complexity, it didn't let go. When you think about it, the chemistry of life is as much about sustainability as it is about survival. Other branches of chemistry chase transformation, speed, or spectacle. Biochemistry prefers endurance. It loops, recycles, balances, always conserving energy and materials wherever possible. Cells don't waste. They reuse, reconfigure, redirect. Carbon molecules are broken down for energy, only to be rebuilt again into proteins, lipids, or nucleic acids. The chemistry of life is chemistry that knows how to last, and in that subtle efficiency lies its beauty. You are made of the same atoms as the rocks under your feet and the air above your head. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Just a handful of elements with a sprinkle of trace metals. The difference is not in the ingredients, but in the arrangement. In you, they form molecules that move, react, and communicate. They assemble into membranes that hold cells together, proteins that speed reactions, and DNA that encodes memory and potential. Out of that choreography emerges thought, feeling, laughter, and memory, all from the same raw material that builds mountains and oceans. Beneath your awareness, a molecular symphony plays, enzymes working tirelessly, ATP sparking bursts of energy, proteins folding and unfolding with every second. It's not loud, not dramatic. You don't hear it. You don't feel it, but it sustains you with every breath, every blink, every heartbeat. The chemistry of life is chemistry whispered at the smallest scale, a kind of background hum that never stops. And life doesn't just whisper within us. It resonates through the planet itself. The Earth, which looks so solid and permanent, is in fact a restless chemical engine. The mountains we see as unyielding are eroding. The seas are shifting. Gases are circulating, and deep beneath our feet, molten rock is convecting and churning. Geochemistry is chemistry in slow motion, but its consequences shape everything. The saltiness of the oceans, the fertility of the soil, the makeup of the atmosphere, even the temperature of the planet. Volcanoes are some of the Earth's most vivid chemical events. Deep below, rocks melt into magma that holds dissolved gases, water vapor, carbon dioxide, sulfur compounds. As the magma rises, pressure falls, and those gases escape violently, like opening a shaken soda can, but on a scale that can reshape continents. The eruption hurls ash, gases, and molten rock skyward. Yet these events, destructive though they may seem, are part of a vital cycle. Volcanic gases help replenish the atmosphere. Ash weathers into soil rich with minerals. Even the climate can shift as volcanic dust reflects sunlight, cooling the planet for months or years. Chemistry never acts in isolation. It always feeds into broader systems. Once the lava cools into rock, another transformation begins: weathering. Rainwater, slightly acidic from dissolved carbon dioxide, interacts with minerals, breaking them down into clays and releasing ions into rivers and seas. Over time, this gentle chemistry carves caves into limestone, hollows valleys, and enriches waters with nutrients that marine life depends on. A raindrop falling on stone may seem trivial, but multiplied across millions of years, it can wear down mountains and rearrange coastlines. The ions released by weathering, calcium, potassium, magnesium, don't just vanish. They often find their way into the ocean where marine organisms seize them. Shellfish and corals use calcium and carbonate to build skeletons and reefs. When these organisms die, their remains sink, accumulating into thick layers of limestone that lock carbon away for millions of years. This slow cycle of weathering, ocean chemistry, and rock formation is one of Earth's quietest but most powerful systems: the carbon cycle. Carbon is constantly on the move. It drifts in the air as carbon dioxide. It dissolves in the sea as carbonate ions. It flows through living bodies as sugars, proteins, and fats. Plants draw it in from the atmosphere, weaving it into glucose. Animals eat the plants, releasing carbon again with every breath. When organisms die, decomposers return much of their carbon to the soil and sky. But some of it becomes buried, compressed, and eventually fossilized into coal, oil, or natural gas. For millions of years, this carbon remains underground until humans dig it up and burn it, releasing carbon dioxide once again. It is a grand loop, but not a perfect one. Our interventions are tipping the balance, amplifying the greenhouse effect, warming the planet. The atmosphere itself is a complex chemical network. Oxygen, nitrogen, carbon dioxide, methane, ozone, water vapor, all in constant flux, reacting under sunlight, reshaping weather, and influencing climate. Ozone in the upper atmosphere shields us from ultraviolet radiation. Yet ozone near the ground can choke lungs and contribute to smog. Methane, though less abundant than carbon dioxide, traps far more heat molecule for molecule, adding to the warming of the planet. Water vapor cycles endlessly through evaporation and condensation, forming clouds that both reflect sunlight and trap heat. Even a raindrop is chemistry in action, carrying dissolved gases and pollutants from sky to soil. Step back, and the planet looks almost alive in its self-regulation. Weathering draws down carbon dioxide, cooling the climate. Warmer temperatures speed the cycle, releasing more carbon, warming again. The Earth is not conscious, but its chemical systems behave like feedback loops, balancing and rebalancing, finding equilibrium after each disruption. This interplay of geology, atmosphere, and life led some thinkers to suggest the Gaia hypothesis, the idea that the planet itself behaves like a self-regulating organism. Whether or not one accepts that framing, it's clear that life and Earth shape each other constantly. The forests exhale oxygen, oceans absorb and release carbon, soil bacteria fix nitrogen, and volcanoes recycle minerals. And in every part of this planetary ballet, carbon is central. The calcium in your bones was once part of a star, filtered through rock and ocean, and perhaps once held in the shell of a mollusk. The nitrogen in your DNA may have been split by lightning in a prehistoric storm. The carbon in your lungs will, after you exhale, feed a tree that grows silently under the sun. Life and Earth exchange elements in an endless dance, atoms moving from one form to another, one body to another, one age to another. Out beyond our planet, chemistry stretches into the stars. The cosmos is not empty. It is a vast laboratory where atoms collide, fuse, and transform across unimaginable scales of time and distance. In the hearts of stars, nuclear fusion reshapes matter itself. Hydrogen, the simplest of all elements, is crushed together into helium under immense heat and pressure. That process releases energy, lighting the sky, warming planets, and sustaining life. But fusion is more than light and heat. It's a kind of cosmic forge. As stars grow older and heavier, they begin to fuse helium into carbon, carbon into oxygen, and then into elements like magnesium, silicon, and sulfur. Each stage produces layers within the star, like a cosmic onion, each shell fusing a heavier element than the last. This continues until the fusion reaches iron, the element that marks the limit. Fusing iron does not release energy, it consumes it. When a star reaches that point, it can no longer support its own weight. Gravity takes over. In massive stars, this collapse triggers a supernova, one of the most powerful explosions in the universe. For a brief moment, the light of a single star can rival that of an entire galaxy. In the heart of that cataclysm, new elements are born. Gold, uranium, platinum, atoms heavier than iron, are forged in those final moments and hurled across space. They scatter, drifting for millennia, until gravity pulls them into new clouds, new systems, new planets. That is how Earth was seeded with the materials that would eventually become rock, ocean, and living tissue. The iron in your blood, the oxygen in your lungs, the carbon in your cells, all of it originated in stars that lived and died long before our sun was born. To say you are made of stardust is not metaphor, it is chemistry. Between stars, the universe is filled with clouds of gas and dust known as nebulae. They are not dense in the way we think of air, but they are vast. Within these regions, atoms and molecules float, collide, and sometimes stick together on the surfaces of tiny dust grains. Over time, gravity gathers these clouds into denser knots that collapse into new stars, surrounded by spinning disks of gas and dust. Out of those disks, planets are born. And within those cold, dark clouds, something remarkable happens. Chemistry unfolds in slow motion. Even at temperatures close to absolute zero, molecules form. Simple hydrogen atoms pair into H2. Carbon and oxygen join into carbon monoxide. Nitrogen bonds into ammonia. Even more complex molecules arise. Water, methanol, formaldehyde. Radio telescopes have detected over 200 different molecules drifting in space, some of them organic, containing the same building blocks that underpin life on Earth. Amino acids, simple sugars, alcohols, all found floating in the darkness, waiting to be gathered into a new planet's chemistry. It's a reminder that the seeds of life are not rare. They are scattered generously across the galaxy. As stars age and die, they release their material back into the interstellar medium. It's a cycle. Birth, life, death, renewal. The early universe had only hydrogen, helium, and a touch of lithium. Everything else, the carbon in your breath, the calcium in your teeth, the potassium in your nerves, was built later in stars, then flung outward and recycled again. The universe grows chemically richer with each generation of stars, creating the diversity of elements that make planets, oceans, and organisms possible. Closer to home, our solar system offers its own chemical stories. Venus, thick with carbon dioxide and sulfuric acid clouds, is a study in runaway greenhouse chemistry. Mars, thin and cold, has traces of methane that hint at processes we don't yet fully understand. Jupiter and Saturn, gas giants of hydrogen and helium, host storms so massive that lightning crackles across entire hemispheres, sparking new molecules in their turbulent skies. Saturn's moon Titan, with lakes of liquid methane and nitrogen-rich air, is a natural laboratory of organic chemistry, alien yet tantalizingly familiar. Even comets, icy wanderers from the edges of the solar system, carry frozen water, carbon dioxide, and organics. When they swing close to the sun, they release these compounds, leaving luminous tales that whisper the story of chemistry preserved since the birth of the solar system. Exoplanets orbiting distant stars reveal yet more. When starlight filters through their atmospheres, astronomers detect the fingerprints of gases, water vapor, methane, carbon dioxide, sometimes even oxygen. Each discovery suggests possibilities. Could there be life there, stirring in oceans beneath alien skies? Or are these planets barren, chemical landscapes with reactions that never quite crossed the threshold into biology? We don't know yet, but the chemistry speaks, and we are learning to listen. When you look at the night sky, you're not just seeing light. You're seeing history written in atoms. Photons that began their journey millions of years ago. Molecules forged in stars long gone. Elements scattered across space that eventually became you. The connection is not abstract. It's intimate. The same forces that shaped galaxies also shaped your body. The same reactions that ignite stars also spark in your cells. Chemistry is the thread that weaves the universe together, from the smallest particle to the grandest scale. And yet, for all its grandeur, chemistry is just as present in the quietest moments. The cooling of a cup of tea, the fading of a scent in the air, the shift of wood as a house settles. Every stillness holds hidden motion. Molecules vibrate, electrons shift, bonds stretch and relax. Even in silence, even in darkness, matter is alive with invisible rhythms. Over this journey, we've wandered through chemistry's vast terrain. We began with atoms, those tiny centers of protons and neutrons, orbited by restless electrons. We saw how their arrangements and attractions give rise to the diversity of matter. We followed electrons as they leapt, shared, and resisted, forming bonds that build everything from water to DNA. We explored energy, how heat and pressure drive reactions, how catalysts offer shortcuts, how balance emerges in equilibrium. We walked through acids and bases, mixtures and solutions, slow reactions and sudden explosions. We saw chemistry at work in life itself, proteins folding, DNA copying, ATP sparking energy into every movement. We saw it in the earth, volcanoes, weathering, oceans, and air, and we lifted our gaze to the stars, where fusion builds elements and nebulae scatter seeds of life. Through it all, one truth repeats. Chemistry is not an event. It is a process. Not a moment, but a continuum. Not separate from us, but the fabric of us. Think of it this way. The carbon in your breath today may one day drift into a tree, then into soil, then into limestone, then into the mantle of the earth, then into a volcanic plume, then into the sky again, then into another creature, and perhaps one day into another world. Atoms outlive us. They move on, continuing their chemistry in new forms and new stories. In that sense, nothing ever ends. Everything transforms. And perhaps that's the quiet comfort chemistry offers. The world may feel chaotic, but at its heart, the rules are steady. Atoms seek stability. Energy flows from high to low. Reactions balance and rebalance. From stars exploding to tea cooling. From DNA copying to rocks eroding. Chemistry is both change and constancy. It's the pulse of the universe, felt in every object, every organism, every moment. So, as we close this exploration of the chemistry of nearly everything, remember this: even when nothing seems to be happening, chemistry is still happening. The atoms are still dancing. The molecules are still mingling. And the world, even in stillness, is beautifully, endlessly alive.